a semiconductor a good conductor, we introduce impurities in the pure crystal. There are two types of impurities that are added. If the impurities are pentavalent, then the resulting semiconductor is N-type. In N-type, electrons are the majority of charge carriers, and if the impurities are trivalent, then the resulting semiconductor is P-type. In P-type, holes are the majority of charge carriers. Now, if we join them, then at the junction, the electrons from N-type will fill the holes in P-type, depleting the charges near the junction. This region is known as the depletion region. If we connect P-type to the positive terminal and N-type to the negative terminal of the battery, then the depletion layer reduces, and this is called forward bias. If the polarity of the battery is reversed, the depletion layer increases, and this is called reverse bias. Mosfets are of two types, enhancement type and depletion type. Both of the types are further divided into two types, N-channel and P-channel. In this video, we will look at N-channel Mosfet only. First, let's see the N-channel enhancement type Mosfet. This is the structure of Mosfet. The yellow regions are N-type semiconductors and blue are P-type semiconductors. This terminal is connected to the substrate or body, hence it's called the substrate or body terminal. These two terminals are called source and drain terminals. Between these terminals, we have a thin layer of insulator or dielectric. Above this insulator, another terminal is attached. It is called the gate terminal. These are all four terminals of MOSFET. As the MOSFET is symmetrical, that is, the source or the drain can be interchanged. Hence, the source terminal and substrate terminal are connected internally, and the MOSFET we see has three terminals. Also, this stops any current flow from the substrate to the source as they are at the same potential. Now, in the MOSFET, we want to flow conventional current from drain to source. So, let's connect a battery between drain and source. This voltage is called VDS as it's between the drain and the source. Also, we can see the graph of drain current versus VDS. The positive end of the battery increases the potential at the drain terminal, thus increasing the depletion region between the drain and substrate. Due to this, there will be no current flow from the drain to the source and the MOSFET is off. This is also called the cutoff region. Now to flow current from drain to source, we have to create a channel between them. To create the channel, we connect a small voltage source between the gate and substrate with the positive terminal to the gate. This voltage is called VGS as it's between the gate and the source. The substrate is a P-type semiconductor, hence the charge carriers are holes, but there exists some free electrons as minority charge carriers. The battery creates an electric field inside the substrate. Due to this field, the electrons in the substrate flow opposite to the electric field, that is, towards the gate. Due to the presence of an insulator, these electrons cannot flow from the substrate to the gate and thus they accumulate near the gate and the substrate. We know that the capacitor is used to store charge on two metal plates. Also, we can increase the capacitance by placing an insulator or dielectric between the plates. Similarly, the insulator or dielectric in MOSFET not only blocks the electrons, but also increases the charge on them, thus attracting more electrons. Now, if we increase VGS, more electrons get attracted towards the gate, and these electrons start filling some of the holes. Also, due to the stronger positive charge of gate, holes start moving away from the gate. Now, in this region, we can see there are no holes, but we have free electrons. Due to these electrons, the region near the gate becomes negative, or an N-type semiconductor. This creates a channel that connects the source and the drain to each other internally. In effect, we've created a pipe between the source and drain, so that electrons can move from the source to the drain. The thickness of the channel can be controlled by changing the gate voltage. As the voltage increases or decreases, the width of the channel also increases or decreases respectively. The voltage at which the channel is formed is called the threshold voltage. As this channel is created, now we can flow current from the drain to the source by the channel. The flow of conventional current is from drain to source, but the flow of electrons is opposite to it, that is, from source to drain. This is also the reason why they are called the source and the drain, because the source supplies electrons to the channel and the drain collects the electrons from the channel. As the conventional current flows from drain to source, it is called drain current. Now the MOSFET is in the ohmic or linear region. In this region, it follows Ohm's law, that is, as the voltage increases, the current increases linearly, but as the voltage decreases, the depletion region between the drain and substrate will increase as they are reverse biased. Also, the channel begins to deplete towards the drain end. This is because the drain is at a positive potential. The negative charges from the channel closest to the drain are being pulled into the drain. This reduces the width of the channel, restricting the flow of charges and reducing the flow of current. As we increase the voltage, a point will be reached when the channel is completely pinched off. This is called the pinch-off effect. In real cases, the channel is not completely pinched off. Due to the large flow of electrons in the channel, the number of electrons will keep the channel. Hence, instead of stopping the current, there is a constant saturated current. This current is called saturation current, and the voltage at which it occurs is called saturation voltage. Now if you increase the voltage, the reverse biasing will increase and the channel will further decrease, but the current will not increase because it's saturated. This is known as the saturation region. But if you still want to increase the current in the MOSFET, how will you do it? Now that you've thought about it, let us see it in animation. As you may have remembered, the width of the channel is controlled by the gate. Hence, by increasing the gate voltage, we can increase the width of the channel. Now if we increase the voltage, the current will also increase. Again, at a certain voltage, pinch-off will occur and saturation will occur. Then, again increase the gate voltage. MOSFETs are also called voltage-controlled devices because the amount of voltage at the gate controls the flow of current from drain to source. Also, there is no current flow from the gate. If you have noticed, the two graphs that we created are the characteristics of the MOSFET. This is the drain characteristics and this is the transfer characteristics. There is another type of MOSFET called the depletion type. This is similar to the enhancement type, except the channel is also formed while doping. That is, the channel that was formed by the gate voltage in enhancement type is present by default in depletion type. All other working principles are the same, except that the depletion type requires a negative gate voltage to turn on. It is normally on, while the enhancement type is normally off. Now you know how a MOSFET works. Let's look at its circuit symbols. There are four terminals: source, gate, drain, and substrate. The gate is not directly connected to the substrate. An insulator is present. Hence, the gate terminal is floating in the symbol. Source and substrate are connected internally. Hence, we connect the source and substrate in the symbol also. If the lines are broken, then its enhancement type as the channel needs to be formed. Else, if it's one solid line, then the channel is present in its depletion type. If the arrow is pointing towards the substrate.
So this is showing the difference between enhancement and depletion type MOSFET based on their symbol, their icon. So for N-channel enhancement, now this MOSFET symbol will vary depending upon the source. However, this image shows it's a gate, which is this part of the MOSFET. That's the middle part. And then this is the drain, and then this is the source. And the author indicates that the source is connected to the substrate internally to the MOSFET. Now, this area here between the drain and the source, you notice it has these open gaps in it. And that basically identifies this as an enhancement type, which means that it needs a voltage from the gate to the source in order to get current to flow from the drain to the source. The lower MOSFET, this is a depletion type MOSFET. It has a gate, has a drain, has a source, and the source is connected to a substrate here. However, you notice there's a complete line here. So depletion MOSFETs are always on, and enhancement MOSFETs are always off. And MOSFETs come in N-channel and P-channel. P-channel also has a source and a drain, and this is an enhancement PMOS. It still has this broken gap. So the way the MOSFET works is the channel forms under the gate, and that allows the holes to basically flow from the drain to the source.
Then it's N-channel, where the electrons flow towards the gate to form an N-channel. Otherwise, it's P-channel, where the electrons flow away from the gate to form a P-channel. These MOSFETs are present in almost all electronic devices, and they need electricity to work. Watch this video on how the mobile charger works, or continue by watching this video.
named as source, drain, and gate. Construction of basic design of Mosfet is quite simple. Just take a block of P-type semiconductor This block will be your base for Mosfet. We also call it as substrate, and the entire Mosfet we will fabricate on this base. Now, two portions on the same side of this P-type substrate are made highly doped with N-type impurity, as these are shown here in the figure. Source and drain terminals are brought out from these two end regions as shown. Now, the entire surface of the substrate is coated with a layer of silicon dioxide. Silicon dioxide will behave here as insulation. On this layer of silicon dioxide, a thin metallic plate is placed. This metallic plate will act as gate contact to the substrate. The gate terminal is brought out from this metallic plate. Hence it is seen from the figure that gate contact is insulated from the substrate, but drain and source contacts are directly connected to respective N-type regions. This was the constructional feature of a Mosfet. Now we will come to the operational features of Mosfet. For that, we have to connect on DC voltage source between these two N-type regions. The N-type region connected with positive terminal of the source is called as drain, and the N region connected with negative terminal of the source is called as source. As soon as the drain and source are connected with DC voltage source, there will be two PN junctions formed. One is in between N-type drain and P-type base, and the other is in between P-type base and N-type source. As drain is connected with positive terminal of the source, the drain is in higher voltage than base. Hence, this PN junction is reverse biased. On the other hand, as source is connected with negative terminal of the battery, P-type base will be at higher potential than N-type source. Hence, this PN junction is forward biased. As between drain and source, there will be one reverse biased and one forward biased junction. There will be no significant current flowing from the drain to source, but a tiny current continues to flow due to minority carriers. We can say that virtually there is no continuous path or channel between drain and source. Now let us see what happens if one suitable positive voltage is applied at gate terminal of the device. In that case, due to attraction of positive potential of gate contact plate, negative free electrons, that is minority carriers in P-type base, will be accumulated towards a contact plate and form a channel of negative charge carriers, even inside P-type semiconductor.
So at this point, the drain is connected to a positive voltage, the source is connected to negative, and then a battery is brought in and connected between the gate and the source or ground right here. So when that happens, these elements that are actually floating around in the P-type substrate, they start, and we increase this voltage between the gate and the source. These elements start moving up below the gate, and they start forming a bridge, electronic bridge between this drain and the source. And once this voltage gets high enough, basically there's a path for current to flow between the drain and the source. So the Mosfet, this battery here is called gate to source voltage here, and the authors mentioned something called terms called saturation and pinch off. So is when our gate to source voltage gets so high that this channel basically begins to close on one end up here near the drain, so it starts to shut off. But in the MOSFET, at some point, the gate to source voltage is high enough so that this channel becomes open. It becomes stuck open. That's called saturation, which means there's still a very small path of current to flow between the drain and the source. So this brings up a difference between MOSFETs and BJTs. MOSFETs operate in saturation, whereas BJTs operate in what we term the active mode. So when you hear the term saturation, difference between MOSFET and BJTs, you don't want saturation in a BJT, but you do want saturation in a MOSFET device. So this little channel here, if the gate to source voltage is removed, the channel vanishes, and the piece type just has these electron negative parts just kind of moving around randomly.
This channel, due to higher concentration of free electrons, will behave as N-type semiconductor, although entire base is doped with P-type or trivalent impurity. It is obvious that the number of free electrons accumulated towards gate contact plate depends on the strength of positive potential given to the gate terminal. Hence, width of N channel depends on the voltage applied at gate terminal. More the applied voltage, greater the width of the channel, means greater the conductance between drain and source. Here we have seen that there is no direct connection between gate contact and substrate. Instead, these are insulated from each other. But due to electrostatic attraction, the conducting channel between drain and source is formed, and because of that, the channel is also called induced channel, and the device is called induced channel MOSFET. It is also clear that when there is no voltage applied to the gate of the device, there will be no current from drain to source, except negligible amount of saturation current due to minority carriers. But if the gate voltage is gradually increased by keeping fixed drain to source voltage at a certain minimum applied gate voltage, drain to source current will start flowing. And this voltage is called threshold voltage. So, below threshold voltage, the device will behave as non-conducting or in off mode. And for gate voltage greater than threshold value, the device will be in conducting or on mode. So this type of MOSFET is suitably used as a gate-controlled switching device.
So with that kind of very basic introduction to the physics of a of a MOSFET transistor. And from the presentation, MOSFET has a gate, has a source, and has a drain. MOSFETs operate by using an electric field, and MOSFET is a voltage controlled device. We understand it's controlled by the gate to source voltage. And the electric field basically forms when the gate to source voltage is applied to the MOSFET device. The MOSFET, compared to a bipolar junction transistor, these give some of the applications, amplifiers or switch, and MOSFETs also come in P-channel MOSFETs called PMOS devices. And then the difference between the way they work, MOSFETs are voltage, BJTs are current controlled, MOSFETs are unipolar, BJTs are bipolar. They have different response to noise. MOSFETs have a much higher input impedance. However, one of the characteristics of MOSFET is that these devices are fragile devices, and any of your electronics that you're carrying, mostly portable electronics, a lot of your systems today have millions or even billions of MOSFET devices. In your jump drives that you carry, millions of MOSFET transistors. MOSFETs also have a characteristic that, depending on the type of MOSFET, in digital logic, when you remove power from the MOSFET device, it remembers the state that it was in. So the MOSFET can record and basically hold on to that. And the inventors of these jump drives and other recording devices, basically some MOSFETs were just like tape recorders. When you turn off the recording of the tape player, the tape remembers what's on it. The same as MOSFET digital devices. So at the bottom, the control device in MOSFET is the gate. So what's the control device in a BJT? What controls current in a BJT?
Like current, funny.
The base.
The base controls current in the BJT. And MOSFET, the drain, in-channel MOSFET, the drain controls the output current. And what controls the output current in the BJT?
Collector.
We're kind of pointing to it here. The collector. And then the source, which basically gathers the moving electrons in MOSFET. In BJT, the emitter, this is where the electrons leave the MOSFET. The current comes out of the emitter. So in terms of operation now, this idea that MOSFETs are fragile has to do that these devices are static sensitive devices, which means they can be damaged by static charge. And if you've ever been tempted to change memory in one of your computer devices, you're very aware that you avoid ever touching the metal pin on any kind of microprocessor or digital memory devices, because those devices are filled with MOSFET transistors, and if they get static charge discharge, it can damage the gate on devices. So that's what it means here when it says fragile. BJTs are not like that. They don't respond to static electricity like that. So comparative GM of a BJT. What does GM provide in a BJT? So what's the purpose of G sub M in a BJT?
It's a game.
What? Say that? GM?
Never mind.
It's transconductor of the device. So if we want to increase the gain in a BJT, we can either increase the GAM, GM MOSFETs are worse than BJTs with this, which means MOSFETs need more current to increase the GM. The speed, BJTs can be designed at very high speed, high frequency. MOSFETs kind of in the medium here, although you have computers and things running into gigahertz at this point. Noise, MOSFETs, BJTs generate noise, but MOSFETs are more worst case. They generate lots of amplified noise. As a switching device, and this goes to digital, all MOSFETs are used in digital devices. BJTs, when they switch, they're not the best in terms of the speed of switching, whereas MOSFETs can switch very fast. The higher Z impedance of the gate, BJTs have a low impedance on the base. MOSFETs have input impedance in megohms on the gate. And then ESD sensitivity, MOSFETs are definitely more sensitive to ESD compared to the BJT transistor. The MOSFETs, the authors were referred to an oxide layer. So this is called, what's the oxide layer in a MOSFET?
Is it like the?
So we're kind of reviewing those presentations. The word oxide layer was mentioned several times.
Is it the top layer where it connects?
It's a layer beneath the gate on a MOSFET. And the oxide layer acts like a capacitor in a MOSFET device. So it reduces power consumption, which means there's no gate current in a MOSFET compared to a BJT. MOSFETs are very fast at switching from digital. A lot more noisy, amplified noise. So the MOSFET usage, that doesn't mention digital here because we're basically interested in using the MOSFET as amplifiers, not so much as digital gates. But you noted that the lower part says the MOSFET is used in digital CMOS logic, and it uses P and N channel MOSFET for that. And the types of field effect transistors, you have JFET, MOSFET is an insulated gate bipolar transistor. There's an organic field effect transistor, and then there's a nanoparticle organic memory FET. And since this presentation was given, there's actually other versions of types of field effect transistors. So this is kind of a list of transistors that operate off of the electric field that's created when voltage is applied. So voltage control device, low power dissipation, and your voltage control switches, BJTs, are current control switches. And this is a different, artist's idea of a MOSFET device. What is this area here called? Large kind of green area. What is that?
Substrate.
Substrate. Substrate. Well, the substrate or body is there, and then there's a metal pin attached to it on the bottom. It shows here this block of silicon here, and this area here, this blue area, this is the area for the N channel that's embedded in this substrate. And in the middle here, this is the gate, middle of the gate. So this gate has a width and it has a length, L. And we'll find that the width and the length are used to control the current in the transistor. And then we notice here this silicon oxide layer. It's underneath the gate right here. So designing a MOSFET transistors, when using MOSFET, the designer can have the free option of changing the width and length of the gate. And these dimensions are not all the time rectangular, and you can also have multiple gates on a MOSFET. So BJTs are usually fixed, and they're designed. However, if you're a design engineer using MOSFET, you could be at a point where you can actually design your own new MOSFET devices. So this is showing a side view of the body of the MOSFET, a P-type substrate. And we notice here this L of the gate, and then the gate, and then the width especially, we don't have it there. Drain and source may be interchanged, and recall that statement there. Can we interchange the emitter and the collector of BJT? And we understand we not interchange those because they have different forward bias restrictions. Designing MOSFET TOX, this is the oxide thickness. That's another important parameter that we have here. So this channel here is just saying that PN junctions must be kept reverse bias. Whereas compared to a BJT has a forward bias basic emitter and then a reverse bias collector base. The body, which is this terminal, if it's an NMOS, it should be connected to the most negative voltage level. If it's a PMOS, the body must be connected to the most positive voltage level. And this is one of the kind of the simplest ways to damage a MOSFET transistor is by not paying attention to where the body is connected. If you recall from the presentation, engineers, the method that's used to reduce the opportunities for damaging the body part of the MOSFET is to, what do we do to the fourth terminal of the MOSFET, which is the body? Where are we connected to?
To the source?
This is our gate. So what we're doing, yes, we take that and then on the icon, make a little arrow and we connect that to the body, and then we connect this to the source. So that basically takes care of inadvertently not following these instructions for NMOS and PMOS. That's a creative idea to do that. The body is usually connected most negative in the case of P substrate, or positive in the case of N-type substrate. And at the bottom here is just saying that this source is usually not optional when you go into P-SPICE. You'll find some MOSFET models have an open source or an open body terminal, and some have a terminal already shorted to the substrate. This thin channel under the gate here. So we're talking here about when we apply a gate to source voltage, a channel starts to form under, with the electron starts to form under the gate. So under certain bias conditions, this thin channel can be formed under the silicon diode insulated layer, and that will electrically connect the drain to the source. And this depth of the channel, again, the way the presentation was doing, it basically was saying that this channel forms when we put the right gate to source voltage on it, and then if we keep applying more and higher gate to source voltage, this channel is thicker and thicker on here. And it's just like a pipe. The larger the diameter of the pipe is, the more the water flows through that pipe. So this depth of the channel is controlled by the gate voltage. And the length of the channel and the width of the channel are important design parameter in the MOS MOSFET device. So this metal piece for the gate, this has a width and a length, and then that's used to control the depth of this channel in the MOSFET. What happens to this channel when the gate voltage is 0 volts?
It doesn't.
What is it?
It doesn't let
It
flow
collapses.
go through.
Okay. When gate voltage is 0, this channel collapses, and the enhancement MOSFET returns to an off type switch. So this MOSFET, here's another MOSFET symbol you might you can come across. It doesn't even identify the source and the drain. So over here, when the gate voltage is, now this term here, that we come across this statement during those presentations. It says magnitude of G sub S, gate to source, is less than the magnitude of V sub T. What was the term given to V sub T? Now, in a BJT, we had a term called V sub base emitter. And what is that number equal to for a practical NPN BJT?
0.7.
0.7.
Is equal to 0.7. In a MOSFET, the term is called V sub T. I was asking, what's the name given for V sub T? Now, it's similar to the base emitter for in a BJT, we call this the turn-on voltage. In a MOSFET, we call this the threshold voltage instead of the turn-on voltage. But a MOSFET doesn't actually turn on, it basically gets to this point called the threshold. So when the gate voltage is 0, the MOSFET behaves like an open circuit switch. When we apply a 1 or some voltage to the gate, the MOSFET becomes a variable resistor. And this symbol doesn't have an arrow to it. That's usually how you draw a variable resistor. So when the gate to source voltage is greater than the threshold, the MOSFET NPN enhancement is on. Now that's different from a BJT where we say BJT base emitter is on when there's 2.7 volts across it. A MOSFET is on when the gate to source voltage is greater than the threshold. The enhancement MOSFET is on when the gate to source is less than the magnitude of the threshold voltage. So it's basically a given MOSFET, and this is another kind of a simple animation here. It shows the body, P-type body. There's some embedded drain material, embedded source material, and then there's a gate, metal gate structure here. And then the substrate usually is taken to ground. And if we ground the source, remember we had that in one of the images. So we connect the source to ground. And then next, we connect a gate to source voltage, and that creates an electric field under the gate here. And that's very different from the way a BJT operates. There's no electric field created when the BJT model we discussed. And then we place in a drain to source voltage. And once we get a drain to source voltage, the electrons negative electrons can move from the source to the drain. Remember, holes are actually responsible for the current from the drain to the source. And a reverse current carrying the negative electrons move from the source to the drain. And then this is the channel that's created under the gate. What is this area here?
The semiconductor? Or the.
What do we call that area under the gate?
Insulator.
That's the silicon oxide insulator. gate oxide. These are really stretched your imagination because this is definitely a microscopic device. MOSFETs can be much smaller than a BJT, even at microscopic dimensions. The steel can be much smaller. So the channel region contains the electrons. Once we form a channel, we can develop a current I sub D, and we'll find the equation for the drain current of MOSFET are very different from a BJT device. So electron motion is a perpendicular electric field. This, if we were taking maybe a semiconductor physics course, we would be talking about an electric field, and we'd be talking about integrals. How do we integrate the electric field? So, if we were actually getting into modeling the MOSFET device real reality, we basically have to bring up the electric field. We would go use the electromagnetics. Now, but we're not basically going into the physics of the MOSFET devices. We're just basically getting a basic understanding of how this transistor, what conditions have to be there for this transistor to actually become an amplifier. So the drain current is controlled by the gate, the source voltage. And the authors drew one of the curves showing the gate to source voltage versus the drain current. Now, this is another version of showing the MOSFET with and without the no gate voltage here. The electrons accumulated cannot pass under the gate, and when we put on voltage on the gate, the electrons can now move freely between the drain and the source, and then on the gate we develop a positive charge on this plate of the capacitor, silicon oxide. This is indicate electric field pushes P-type hole. But again, to actually design circuits with a MOSFET, the part we really want to understand is that if you do not have any gate voltage, there's no channel under the gate. And then in order to get this channel under the gate for current flow, we have to apply a gate voltage, and then we need to apply a drain to source voltage. So there's our positive gate voltage. Now your equations for the MOSFET. MOSFETs can operate in a triode or a linear region, and they can also operate in a saturation or active mode. And what's the third mode for MOSFET?
Off mode?
It's an off mode, so we don't need to have a plot for the off mode here. So in triode mode, and on your formula sheet, you definitely want to have several formulas so we can decide which mode the MOSFET is in. If the MOSFET is in triode, the gate to source must be greater than the threshold, and the drain to source is less than the gate to source minus the threshold voltage. So the lower part, this is a manufacturer's curve of a particular MOSFET devices. So on the x-axis, this is the drain to source voltage, and then on the y-axis, this is our drain current here. So gate to source less than the threshold voltage, and then we'll have some known threshold voltage, and then the gate to source, drain to source is less than the gate to source minus the threshold. If this is true for this MOSFET, we can draw this line on the curve here, and usually manufacturers will do that. So if we're in anywhere on this side of that line, the MOSFET is in linear region or it's in triode mode. If the MOSFET is in saturation, what we came across was that if the gate to source voltage is increased too high, or the drain to source is increased too high, the MOSFET begins to saturate, which means that this drain current basically flattens out right here, and it doesn't, and the drain to source voltage keeps increasing, and it stays in saturation, so it gets a fixed output. Now there's some advantage to that compared to DJT devices. And over here, this is the gate to source minus the threshold voltage. So for this device, the gate to source voltage minus the threshold is equal to 7 volts. And then here it's equal to 6, 5, 4, 3, 2, and 1. So if we want to increase the drain current upwards, we increase the gate to source voltage. So with this, the design here went from 1 volt gate to source minus the threshold up to 7 volts. And then we kept increasing the drain to source voltage. The MOSFET goes into saturation. Now we note the equations now compared to a BJT. When we calculate the collector current of a BJT, if a MOSFET is in linear or triode, this is our equation to calculate the drain current. If the MOSFET is in active mode, you notice this is called active mode for saturated MOSFET. This is the equation for the drain current. Now what can we kind of pick out from these two sets of equations if we try to solve? We'll try to solve them on paper, but what can we expect from these equations? What's our equation for I sub C and a BJT? What's the equation for collector current in the BJT?
Is it
alpha the current, and beta times the base current.
Related to beta.
beta times?
Isn't it beta times the base current?
Equation for the I sub C.
Or is it?
Relates I sub C to I sub E. We're assuming alpha is not 1. So what's the equation?
Oh. Beta over beta plus 1 times alpha?
Beta times what?
The base current, I sub B?
I sub B. So when we solve this equation, how many solutions do we get? When we solve this equation, so it's kind of a linear equation. However, we're questioning how many, when we solve this equation, how many versions of it do we have to solve? There's only one result for this I sub C, and that's what the inventors of the BJT transistors came across, that out of thousands of transistors, this equation always held. I sub C was beta, I sub D. Now in MOSFET, these are the two drain equations, basically similar to I sub C. However, what these two equations, how how many results can these equations predict? And how do we become aware? Math, this is all math now. Math, MOSFETs convert into math device. So what are these equations in mathematics, not MOSFET, what do these equations tell us about how many solutions we can get?
Maybe
A lot more? Because let's see.
All right, remember our quadratic equation?
Yeah, is it,
Alright, so on the saturation or active mode, we have a square term.
so we have two solutions?
oh, so
So when we
Two?
square something here, you might read a quadratic equation. And then over here, in this drain, depending on how we manage the math here, and again, this is all math, right? So with MOSFET, we're basically have the situation where MOSFETs are more mathematical devices compared to BJTs. And which means MOSFETs are definitely going to require some refresher of MOSFET of quadratic equations. So that's what these equations are predicting. You get more than one solution, and then you have to decide which is the best solution, or which is the correct solution for that device. Now the components in here, let's say for saturation mode, I sub D is mu sub n COX divided by 2 times W over L, that's the width of the gate, times D sub gate to source minus D sub threshold squared. Then there's a term 1 plus lambda D sub drain to source. Later we'll find that usually we can arbitrarily decide that lambda is equal to 0, and then we don't have to carry that term. COX, this is the capacitance of the oxide in the transistor. So the conditions for MOSFET to be in saturation, the gate of enhancement in MOS, the gate to source must be greater than the threshold voltage, the drain to source must be greater than the gate to source minus the threshold voltage. And on this graph here, it shows the saturation region. The region where the MOSFET will amplify is in the saturation region. This is where it becomes an amplifier. If the MOSFET is in the linear region, it acts more like a resistor, a variable resistor, and not an amplifier. So the key to, when we covered BJTs, we talked about operating points. So MOSFET, the operating points would be away from this linear triode region of a MOSFET. So that's the design area. Now these are going to go through the conditions. This is MOSFET enhancement transistor. So this first drawing is showing the P-type substrate, and it's showing the configuration of the MOSFET. Notice it indicated that the oxide was coated onto the substrate, and now the robots go in and actually remove the oxide from here, and they leave metal connected here. So now this drain has a metal contact, and the source has a metal contact. And then on the P-type substrate, we put another metal contact, and now we have our metal contact. So here, MOSFET on is when we have a channel under the gate oxide, and electrons can flow. We have from the drain to the source. The gate voltage is greater than the threshold voltage. Some of the symbols, and you can check these in PSpice, and there's actually another simpler symbol that we're going to be using. How do we know it's a PMOS or NMOS? We'll have to be careful to analyze the drawing and compare it to another source. So this is a Mosfet NMOS enhancement transistor. So here the source is connected, the arrow points out. We notice on the PMOS the arrow points in. And in this version,